As the 4th of July approaches, thousands of fireworks will light up the sky. Glittering greens, sparkling silvers, and rocketing reds. Nothing screams celebration quite like fireworks. All over the world, these colorful explosions are a regular feature of national holidays, religious festivals, and the start of a new year. But while they may mesmerize us with their vibrant displays, fireworks also release harmful substances into the air. The chemistry behind fireworks has a sinister side. So what's behind the dazzling light of fireworks that makes them a significant hazard to human lives and the environment as a whole? Before we look into that, let's first go back in time to where fireworks originates from. Many historians believe that fireworks were originally developed in the 2nd century BC in ancient Luoyang, China. It's believed that the first natural firecrackers were bamboo stalks that, when tossed into a fire, would burst with a loud bang due to the heat building up in the hollow air pockets. The Chinese thought these natural firecrackers would repel evil spirits. Later, between 600 and 900 AD, legend has it that a Chinese alchemist mixed potassium nitrate, sulfur, and charcoal to create a black, flaky substance, the first gunpowder. This powder was poured into hollowed-out bamboo sticks and later stiff paper tubes, creating the first man-made fireworks. In the 13th century, fireworks made their way to Europe, where they gained popularity by the 15th century for their use in religious celebrations and public spectacles. The Italians were the first Europeans to master the art of firework production, and European rulers were especially fond of the use of fireworks to enchant their subjects and illuminate their castles on important occasions. Early US settlers brought their love of fireworks with them to the New World, and these colorful displays played a significant role in the first ever Independence Day celebration, a tradition that continues to this day every 4th of July. As the American spirit of celebrations grew, politicians in the late 18th century leveraged firework displays to draw large crowds to their speeches. Fireworks have also become a lucrative entertainment industry, generating both dollars and smiles. Thunder over Louisville, one of the country's largest fireworks displays, is a testament to the economic impact. According to a study done by the Derby Festival, Thunder over Louisville generates over $56 million for the local economy. But what is the science behind this sparkling display? Fireworks are a testament to the wonders of chemistry and physics. They are a practical application of these sciences, resulting in a spectacle that delights audiences worldwide. Chemical compounds play a crucial role in the creation of fireworks. The combustion process is at the heart of every firework, and it involves a carefully orchestrated sequence of chemical reactions. One of the key components of fireworks is black powder, also known as gunpowder, which serves as the propellant. Black powder is a mixture of sulfur, charcoal, and potassium nitrate. When ignited, it undergoes a rapid combustion reaction, releasing a large amount of energy in the form of heat and gas. This energy is responsible for propelling the fireworks into the sky. The most common type of fireworks is the aerial shell, which is fired from a mortar tube. These fireworks typically have 4 components: a lift charge, a time delay fuse, a braking charge, and a light effect generator. The lift charge is generally black powder, a compound that burns rapidly and propels the shell from its tube. The lift charge also ignites the delay fuse when it fires. The delay fuse is usually a black powder fuse with a delay of a few seconds and is designed to ignite the brake charge when the shell reaches the appropriate height. The purpose of the brake charge, which sits at the center of the lofted shell, is to explode, thereby igniting and scattering the shell's contents. The brake charge is a finer grained and more confined black powder which detonates the shell, releasing the payload. This payload consists of small spherical pellets of pyrotechnic composition, designed to produce light and color. These pellets burn from the outside in, and color changes are achieved by layering different compositions. To produce the dazzling array of colors, color-producing salts are added to the black powder. These salts contain metal ions that emit characteristic colors when heated. When these metals are heated to the right temperature, electrons momentarily jump between the so-called electron shells, or energy levels within the atoms. When they fall back to a lower state, a photon is emitted, and the wavelength of the photon determines the color. For example, strontium compounds produce a vibrant red color, while barium nitrate gives off a green hue, which are some of the easiest firework colors to achieve. Blues are more difficult because the temperature of the reaction has to be just right. Sparks, in contrast, are made using slower burning mixtures, and shapes such as rings, hearts, and smiley faces are made by precise placement of the pellets within the shell. Metals play a crucial role in fireworks not only for their ability to produce vibrant colors, but also for their contribution to the overall performance of the fireworks. Aluminum powder, for instance, is often used as a fuel additive to enhance the brightness and intensity of fireworks. When ignited, aluminum reacts with oxygen in the air, producing a brilliant white light. In addition to their visual effects, metals also contribute to the sound effects of fireworks. Small metal particles such as iron fillings or titanium flakes are added to create the crackling and popping sounds that accompany the burst of light. These metals rapidly oxidize and release energy in the form of heat and sound, adding an auditory dimension to the fireworks display. The speed of a firework reaction is influenced by several factors, including the composition of the shell and other physical characteristics. Some of the key factors are smaller grain size of the components, which result in faster reactions, presence of accelerators like sulfur and sugars or retarders like salt, high pressure or confinement, which increases the reaction rate, packing density, which can reduce the reaction rate, and level of moisture present. However, as firework displays have grown bigger and more widespread, scientists have tried to understand the environmental impact of launching these burning chemicals into the skies above us. Let's look at a few of them now. Fireworks release significant amounts of potassium, which accounted for 28% of UK emissions in 2019. Other metals like copper are also released. However, it's really the short-term impact of the intense metal releases during these celebrations that is a concern. A Spanish study in the San Juan Festival found that metals like strontium, a rare pollutant, linger in the air for days after firework events, with levels 86 times higher than normal. Beyond the metals used to produce the colors, burning fireworks also release gases and small particles, nitrogen oxides, and sulfur dioxide. Some of the negative health effects these pollutants have are respiratory problems, worsening of heart disease, eye and skin irritation, reduced immune system function, reduced lung function, and while not directly affecting human health, sulfur dioxide can react in the atmosphere to form sulfuric acid, which contributes to the formation of acid rain. But there's more. Fireworks often contain perchlorates, which are highly reactive chemicals comprised of chlorine and oxygen, which propel them into the air and are also used as rocket fuel. However, perchlorates can have a harmful effect on human health as they interfere with the thyroid gland's ability to absorb iodine, which is essential for the production of thyroid hormones. In 2006, US scientists investigated perchlorate levels in water next to a fireworks display site. They found a drastic increase of up to 1,000 times the normal levels within 14 hours after the fireworks, with a peak concentration of 44 micrograms per liter after July 4th celebrations. This exceeds the US Environmental Protection Agency's threshold of 18 micrograms per liter, which is considered a potential health concern in drinking water. This is particularly worrisome, since firework displays are often held near bodies of water to minimize fire risk, posing a threat to water quality and public health. Fireworks also frequently spark wildfires, especially in hot, dry regions during the summer. A study analyzing wildfires in the western United States from 1992 to 2015 revealed a striking surge on July 4th. Human-caused wildfires increased by nearly threefold on Independence Day compared to the average for that time of year. As a result of these potential dangers, efforts have been made to create safer, more environmentally friendly fireworks that are more sustainable. The emergence of environmentally friendly fireworks, which are composed of biodegradable materials and emit fewer pollutants, is one example of such innovation. These substitutes not only lessen the impact of fireworks shows on the environment, but they also provide pyrotechnicians and spectators a safer and healthier experience. Technological advancements have contributed significantly to the sustainable development of fireworks, in addition to eco-friendly fireworks. The quantity of waste and pollutants produced during a show has decreased thanks to the introduction of computer-controlled choreography and electronic firing systems, which enable more accurate and regulated displays. In essence, fireworks are a combination of chemicals and fuels that produce a colorful explosion when ignited. The colors are created by adding different metals to the fireworks, which burn at higher temperatures and release light energy at specific wavelengths. But while fireworks are enjoyable to watch, they can have a significant environmental impact, and they can also be dangerous to humans if not handled properly. Fireworks are a fascinating combination of science and spectacle. and we hope this video has inspired you to learn more about the chemistry behind them. Before handling fireworks, be sure to check out videos on fireworks safety tips and DIY firework alternatives. It is very important to prioritize safety and responsibility when it comes to fireworks. Thanks for joining us on this journey into the chemistry of fireworks. Do well by sharing this video with your friends and family to spread the word about the science behind fireworks. Happy learning, and stay safe out there.